All right, hey guys, so hey, how's it going, man? How you doing? He was in my engineering class last year, so. Or 2 years ago? Last year? Last year, all right. All right, so I am Dr. Andrew Heintz, so I got my PhD in 2008, but before that I got my bachelor's in chemical engineering in 2004. I currently work at Intel. Does anybody's parents work at Intel? I'm sure nobody in the room, right? All right, so I work at Intel. What must I do? I work in silicon. What do I do?
How long have you been working at Intel? Because I heard they have a very high turnaround.
So I've been there for almost 12 years. So they haven't turned me over yet.
My dad's been there for a long time. I just heard that's huge.
Yeah, I think we talked last year. Doesn't your dad work at Aloha, right? Yeah. All right, so I just click through here, right?
Yep.
Okay, sounds good. So everybody usually when they hear that I work at Intel, what they assume that I do is I work on computers. I'm a programmer or something like that, right? It's actually embarrassing how little I know about how to use a computer, right? Most of you guys probably know how to use a computer more. I can use some like graphical stuff probably way better than you guys can, but in terms of computers, you guys can probably run circles around me. I'm actually a manufacturing engineer. Right, so sometimes if you guys look out that direction, maybe in a cold morning, you'll see some huge pollution smokestacks coming out. Do you guys ever see that to the west when you look towards the beach, right? To be clear, that's actually not pollution smokestack, it's actually just water vapor coming out of our boilers, right? But that's the Intel manufacturing plant, right? We're not boiling that much water just to keep people warm. We are actually using that as part of our manufacturing process. So, and Amy, who you'll hear from a bit later, she also supports that manufacturing. A good portion of the people over at Intel are not people sitting in a dark room coding all day long like you might think. We're actually working on the manufacturing process. We're actually making the chips that go into your computers, right? The i3, the i5, the i7, right? Those are the chips that actually come out of our factory. They go into laptops and you guys use them hopefully to frag people super fast on your computer games, all right? So this is me. I wear a bunny suit every morning when I go into the factory because we keep things in there super clean. And I also graduated from Sunset High School in year 2000, actually. So does anybody have any questions before I go into my talk about that, what I do? Is it pretty clear? Manufacturing engineer, super boring. All right, so I am a wet etch engineer, by the way, which basically means I'm a glorified dishwasher. So, okay. All right, so let me ask you guys this. Well, let me start. Does anybody here want to be an engineer? A scientist? Anybody want to go into business? Oh, that's actually surprising. Usually it's more business people. All right, fair enough. Anybody want to go be like a doctor, like a medical doctor? Well, that's really surprising. 2 hands, really? All right, fair enough. All right, so what is an experiment? No one knows what an experiment is? What's an experiment? It's a test? That's correct. So I'm an engineer. Am I the only type of person who runs an experiment? Do we think doctors run experiments? Do we think scientists run experiments? Right? Do we think business people run experiments? No? Yeah, they definitely do, right? So when I am talking about what we're going to be talking about today, I am not just talking to the engineers and scientists in the room. Obviously, I'm biased towards that. But I'm talking about a skill today that's universally applicable to people who want to go out and do things in the world, right? Even social workers run experiments, right? They go out, they'll change some program, they'll look at the data, how it impacts people, right? So this is a universally applicable topic, okay? So no, not only engineers and scientists do experiments. And you're correct, it's a test. What we're going to be doing is we're going to be changing some variable, and we're going to be looking at whatever that output may be. All right. So what it all really boils down to, especially for engineers and scientists, but also for everybody, especially like if you're a government worker, right? Government, like social worker, I mean, is just time and money, right? So experiments require resources, right? You guys have done experiments in chemistry class where you poured some material into a beaker with some other material. That costs somebody money, right? That costs the taxpayers money, it costs your school money, right? You can't just use that over and over again. But more than anything else, the most limited resource that we have currently is not water, as I may tell you, it's actually time, right? It takes time to run experiments. If we need to run 100 experiments, that's going to take somebody time to run 100 experiments, and you might not have it. So what we always want to do is reduce both cost and waste. We don't need throwing stuff down the drain. We want to improve efficiency and reduce time to market, right? For people like me, if it takes me 2 years to run experiments, that's 2 years that my chip isn't making money in somebody's laptop, right? We're not selling it, we're not making money, and that makes our shareholders very sad, okay? So experimental design, which is what I want to talk about today, is a technique that enables us to efficiently assess the effect of the different variables that we're looking at, and then look at the response. And ultimately, do we just care about knowing information? You're shaking your head. Why do we not just care about knowing information? Correct. And what do we care about ultimately is what we're going to do with that information, right? Just knowing something is great. We can put it in our wallet, but we can't actually do anything with it, right? We want to actually be able to do something and make a decision. So I'm going to talk about something silly and kind of stupid, but I want to talk about, and he's smiling because he knows I used this one last year, right? But we're actually going to talk about something different. So we are going to make the perfect pancake. Does anybody here hate pancakes? All right, so I'm not talking to you then. The one person. All right, so let's think about the perfect pancake, okay? What happens if our pancake's too thin? It burns, right? What happens if it's too thick? That's even worse. You get that cold, gooey, not cooked thing in the middle. That seems gross, right? Also, if it's the wrong consistency, it's not going to pour correctly, which means what? It's not going to cook right. And then, furthermore, the longer we cook it for, or the higher temperature we cook it for, is also going to impact it, right? So we want our perfect pancake to be the right size, the right consistency, and perfectly cooked and tasty. And this isn't just for us, right? Let's say you're a restaurant. If IHOP puts out pancakes that look horrible and are all burnt, how long is that IHOP going to stay in business? Not very long, right? That's applicable towards anything. If I put chips out of my factory that don't work, well, they fired me long ago, but it's not going to be well for anybody, right? So now I need your guys' help. What are the variables? Does everybody know what I mean by a variable? Basically, our inputs are things that can change. What are the things that we think would be important in making a pancake? What? Ingredients? Okay, so our ingredients for pancakes, what are the ingredients for pancakes? Flour and water. That's about it, right? We put butter on and all that other stuff later, right? But it's flour and water, right? Yeah, so basically, we need to make sure that our mix is right. What happens if it's all water and we put in a little bit of flour? Is that going to cook well? What happens if we use all flour and no water? It's not going to pour, it's not going to cook well, right? So that's definitely a factor. What else might be a factor? Temperature, absolutely. Thickness, size, yep, I like it. So what I boiled down to are 5 variables that we care about. Consistency, which is our water-flour ratio. I do realize that you can put other things in there, but let's just stick with that and make it simple. Thickness, diameter, cook temperature, and cook time. So that's 5 variables. So does anybody want to cheat ahead and tell me how many experiments we need to run to figure out the perfect pancake? Does anybody know? 5? It is more than 5. What's that? 25? That's getting closer. All right, so DOE, which is short for Design of Experiments. We're just going to be using that acronym to speed things up. Okay? So in our experiment, what we're going to do is we're going to deliberately change one and just one of those variables, holding all the others the same, so we can get a full picture of what the impact of that variable is. Does that make sense? Right? If we change 5 things at the same time, are we going to know why that pancake came out wrong? The answer is no. Right? What you do is you hold everything else steady and you change one at a time. Okay? So DOE is not just a fancy name. It's actually an efficient procedure for planning the experiments before we even start. Right? Because again, what we don't want to do is spend all of our time running these experiments and not know what we got out at the end. Okay? So in our case, we've already identified the 5 variables we talked about. We want to know how one affects the others, right? Because maybe if, let's think about this, right? It's very easy to understand. If we change our consistency ratio, maybe we don't need to cook as long, so now our cook temperature is just not the same, right? If we know that if we jack up the temperature on the stove, we probably don't need to cook as long, or vice versa, right? So these air variables, not only do they affect the end result pancake, but they can also affect the inputs of each other, and we need to be able to understand that as well. So I ask you again, how many tests we need to do? The required number of experiments is actually calculated using the formula 2 to the n. So in this case, it would be 2 to the 5th, which is how many? Carry the 7. So it's, what's that? 32 is correct, right? So a 2-factor experiment, for example, if we go here, we'll go back in a sec, but a 2-factor would actually require 4 experiments. So what we would do is for variable A, we would change it to the positive, we'd change it to the negative. We'd change it to positive, and then or I did it in the reverse, right? But this one we would increase, this one we would increase. This one we would increase, this one we decrease, this one we decrease and increase, decrease and decrease, and then you get your full matrix. Make sense? So that's why it's 2 to the n. In this case, 2 to the 2, which is 4. That one's simple, we can do that all day long, right? But now we're looking at 5, so we're looking at 32. Okay, so what the design matrix, which is what that thing I just showed, is it shows us all the possible combinations of all of our factors. Okay, so now, and you're not going to be able to see this because there's 32 factors there, right? If we do that chart all the way out, does anybody want to start cooking that many pancakes? I mean, maybe, that's fair, if you do, but the answer is no, we don't have time for that. So ideally, we need to do 32 tests, we get that. But there's a problem. Your teacher only has enough flour and water to run 20 tests. And you only have enough time in the class period to run 10 tests. So what are we going to do, J-Ron?
I don't remember.
Roll the dice and hope we get a C? Works for me, right? No, so the question is, how are we going to decide the most important factors, the most important variables? Right? So where do you guys think we should start? If you were running this experiment, where would you start? What's that? The extremes. Thomas, where do you think we should start?
Just to like maximize the effect of variables. So just like produce the touch of jumps of the.
Yeah, so you look at the max, the min, you're just going to modify one variable. Is that what you're saying? Right, yeah. So that's exactly correct, right? So our objective isn't to fully understand the range of each variable because we're not, so think about it from temperature. Are we really going to do 296 degrees, 297 degrees, 298 degrees? No, because now our 32 experiment just went up factorially, right? Yes, ma'am. That is a fantastic example. When you're drawing a graph, you don't necessarily do everything. You just kind of get enough points. That's a fantastic example, right? So what we want to do is instead look at what the impact of a change of variable is. And that's why in that matrix we looked at the plus and the minus. Now it doesn't necessarily define the plus and the minus. It doesn't say that if you're at 295 then you need to go 294 and 296, right? Maybe you change it 5 degrees, maybe you change it 10 degrees. The point isn't the output that you get. The point is the change on the output that you get. Does that make sense? And then there's something that's really cool that we can do with that. Let's say, what was your name again? Or your not again, what's your name? Kate. So let's say Kate drops the temperature by 10 degrees and your pancake doesn't cook. What do you learn from that? That temperature's too low. So if we go back to our huge matrix here, so this was our cook temp, right? You guys probably can't see the greens and the reds real well, but the greens are the positives, the reds are the negatives. We know now that if you dropped your temperature and it didn't work, what can we do with every single thing that's a red? Get rid of it. So now we just went from how many experiments? 32 to now how many? 16, right? We just cut it in half, right? So now what are we going to do with our consistency? Let's change our consistency down a little bit. If the consistency didn't work, what do? Throw that out. Now we just went from 16 to 8. And we've run how many experiments? 2. Right? So instead of using 16 pancakes or 16 batters worth of pancakes and the time to do that, now we've cut our actual time in half. well, not technically in half because you've used 2 experiment times, right? Let's say we have 32 hours, now we've only used 2 hours and we've killed 16 hours, right? That's pretty cool. All right, so like I said, the answer lies in just looking at the impact of each variable, and that's really what we care about. And then in the end, yes, maybe we do need to decide that Kate needs to cook it at 296 instead of 295, and she can zero in on that. Then she can make her cupcake shop or whatever, and then she can be in business, okay? But the fact is she saved all this time and all this money getting there, okay? So in summary, right, this isn't a very long one, which I'm okay with, okay? So design of experiments is a crucial skill that everybody can use to try to improve whatever process they're working on, right? What do I mean by a process? What is a process?
A way of doing things.
That's right. Processes are steps by which we go about doing something, right? So, and then I already talked about this, right? But do only scientists and engineers care about DOE? Absolutely not. Business majors look at impact to markets, right? You may even look at it from like a stock market perspective, right? What was the change that some policy had on the stock market? Doctors, absolutely, right? Typically when we think about this, the easiest one for us to think of is drug trials, right? That's always what we start to think about when we're doing experiments, right? Subgroups, looking at people that grew a 3rd arm, you're gonna throw that out. You don't want those people, right? Social workers, like I said, with the program changes, and entrepreneurs, right? Everybody, everybody these days thinks they're gonna be an entrepreneur, right? Everybody's gonna have the next new big thing that's gonna make them $20 billion, right? Entrepreneurs absolutely care about this, not because they're the ones doing it, because they're paying people to run experiments and they don't want to pay people to run 19, they want to pay people to run 3. So even if you're an entrepreneur, you even care about running this as well, right? All right, does anybody have any questions? Because I am pretty much done before we go to the next thing. Does anybody have any questions? All right, I think I only put a couple of people to sleep, so I'll take that as a win. All right. So before I get out of here and hand this over to Amy, I want to plug my engineering class. So I will be here next Tuesday during you guys don't call it AT period anymore, right? It is AT period? Okay. So I'll be here next Tuesday, the 17th, I'll be here during your AT period. And what I want to present is the engineering class. This will be the 5th year that we've run this here at Sunset, which is amazing. I can't believe I'm that old now, right? But what we do in this engineering class is very simple. I'm an engineer, I went here, and when I went to school, I didn't realize how much I didn't know, right? And I don't mean in terms of facts. I'm not gonna teach you how to be an engineer in this class, but what I'm gonna do, or what I want to do, is give you a good idea of what the engineering field is. We're gonna look at various types of engineering, so we're gonna go over the basics. The gentleman who was up here just before said it very aptly. He said that if you're gonna go be an engineer, the first 2 years of your schooling are the same, and that's roughly accurate. The problem is, if you decide 2 years into school that you want to be an engineer but you haven't been taking engineering classes, you basically have to push the reset button. If you start as an engineer and decide later that you don't want to be an engineer, you're okay because most of those classes are transferable, right? So what I want to do is give you a good idea from the start what it is like, what it's going to be like to go to engineering school, maybe what types of engineering you want to start with, and give you a good idea with what to do. So I'm going to pick on you since you were in it last year. You want to could you come up?
Sure.
So what did we do last year? What was your biggest memory of last year?
We basically went over the other types of engineering, like chemical engineering, manufacturing. I don't remember all the others, but
yeah, that's fair.
Just going into the different types of it.
Yeah, great. Thanks. Appreciate it. Yeah, so like I said, I won't talk about it too much more, but next Tuesday we'll meet. So the way it works is it's after school on Tuesdays. That's the biggest question I get usually. I had somebody email me last week and they're like, what period is this being offered? It's being offered 12th period, 14th period, whatever, right? 6:30 to 8:30. Course cost is $50 per student, so this runs 1 night a week for the 2nd semester next year. $50 per student. The reason is because we use materials, we break stuff, we blow stuff up, and that's non-replaceable, so we need to be able to pay for that. Plus everybody gets a textbook and a workbook that we go with. Other than that, I teach it, but we also bring in practicing engineers from around. I've had electrical engineers, see who came last year, electrical engineer, manufacturing engineer, Oh, Joy is another chemical engineer. She comes every year. So, but it's great to get to see other practicing engineers, just not myself, who are in. So, does anybody have any questions about that? Okay, I'll have some flyers afterwards if you want to pick them up. But just remember, next Tuesday during AT period, which I think is 1:30.
We'll put the link in your Canvas class.
Perfect. So other than that, that's all I've got. Does anybody have any questions for me about what I talked about, what I do, or anything else? Yes, ma'am.
Does Intel have a robotics branch?
Intel absolutely has a robotics branch. I do not know who they are or where they do or what they're working on, but absolutely they have people working on robotics because we'd be stupid not to. Yes, sir.
Did you ever internship through Intel?
So I did actually, but that's a funny story. So, well, it's not funny, it's sad, but I was in New Orleans when Katrina hit. So we were out of school that semester. So I came back up here because that's where I lived. It was always my plan to go work for Intel, so we made some phone calls and I was able to get an internship that semester. Intel does not actually offer any formal internships for our manufacturing side. The reason is that it takes way too long to get you guys trained up and even take the don't stick your finger in electrical socket type classes that you need to go into the factory, right? We also have problems with people stealing IP, right? We don't want to hire an intern to come in and accidentally slip a USB drive in somewhere and take some information, right? So, but there are other internships available through Intel. I know some of my friends in the past have done ones even for like marketing and stuff like that, but quite frankly, that's no different than any other corporation that you're gonna see, right? If what you're after is the scientific side of Intel, that's gonna be a little harder to do. Yes, sir?
Yes, can you talk a little bit about why you picked the field of engineering and what you're doing and how did you make that choice?
That's great, yeah. So again, so is Keeneland still here? He retired like 2 years ago, right? Yeah, so Keeneland was actually my AP chemistry instructor, and I loved him, I loved the class, and I decided I was gonna go be an engineer, and I'll be honest, chemical engineering was the one at the time that paid the most, so I was like, well, we may as well start high and go from there, right? So I liked chemistry, liked engineering, we went right into it. As far as why I went to Intel, that's also, I was growing up in the late 90s, and Intel was moving up here in about that time. They were building the big factory out there. All the people up here who were moving up here, they were all selling their like small several $million homes in California, and they were moving up here, and everybody had a ton of money because it didn't cost as much to live up here back then, right? So all these like rich Intel people were flying around. I was like, well, I want to go work at Intel because that seems like a pretty smart thing to do. I missed the boat on that one from all the huge stock increases, but still. So yeah, that's why I ended up there. As far as why I went and got my PhD, was also strictly motivated that Intel was only hiring PhDs, because up here we do all of our technology development. So we were only hiring PhDs for what I wanted to do for Intel, so I decided to get my PhD. I also learned about senior year that, because I was also saying there's no way in heck I'm gonna go to school longer, no way in heck I'm gonna pay money to go to school and get another degree and take loans, right? But I found out that for most engineering degrees, actually all engineering degrees for advanced degrees like PhD, you actually get a small stipend and you get TA. So it actually didn't cost me anything other than like my school fees to go to school. I was able to get a TA ship. I lived on, at the time it was $19,500 a year, which is not great, right? That's like top ramen level, but at least you're making progress and you're not going into debt by 50 grand. So that's why I decided that. Yes, ma'am. So I did know I wanted to do engineering. As far as why I ended up at Tulane, that's kind of a good question. I think our counselor at that time just kind of pointed it out. I think it was the third oldest chemical engineering in the country, so it was pretty well ranked. Tulane's engineering school used to be really good. Before the hurricane, it was really good. It's not as much anymore because we lost a lot of departments. But it was a pretty good school at the time. So I ended up down there and ended up getting a scholarship that made it about the same price to go to Oregon State, which is also a very great school. So I decided that if it was about the same price, I may as well take the adventure, right? So, yep, that's how I ended up down there. So does everybody know where Tulane is? Sorry, I didn't say it. Well, it was implied with the hurricane, right? But Tulane's in New Orleans, so which is a really great place to go to school for reasons that you guys can surely imagine, right? So. All right, any other questions? Yes, Thomas.
So,
What's that?
So, like, what things stimulate you to have a class of
why did I start the class at Sunset? I wanted to get involved. When I got back up here, I wanted to do volunteering, but what I found was that most of the volunteering opportunities that were available were not getting to interact with the students who I wanted to, right? I felt that me going and teaching someone how to read as well wasn't necessarily the best use of my skills, and instead I wanted to interact with guys like you who can ask questions and interact back. That was what I wanted to do, and there weren't really programs for that, so I started the program myself. Yes, sir.
Can you talk about Intel's program for promoting women in engineering? I know when I left, they were actively promoting 7 and above. They were trying to get to 50%.
Yeah, well, so I'm not going to comment on corporate programs and stuff like that, especially ones that I don't know as much about, right? But Intel, obviously, like many corporations around the world right now, are actively trying to increase, like you mentioned, female participation. It is well known out there, it shouldn't be a secret to anybody, that there is both a pay and participation gap with females, especially in the sciences, but in most careers, or I shouldn't say most careers, in many of the technical fields, that's the case, right? So Intel is taking active steps to correct that, as are many of Intel's competitors and other corporations around. So as far as the specific programs, I don't feel comfortable speaking to that, especially being recorded. So, all right, anything else? All right, thank you guys.